Here's a beautiful group theory exercise that I'm so excited to share with you. It's a following problem. It basically says that if G is a finite group and if there is an isomorphism from G to G, okay, a homomorphism that is bijective from G to G, such that sigma of x is not equal to x for all x not equal to the identity, and sigma of x is equal to x for all x in G, then G is an abelian group. So we'll actually go over all these concepts. I assume some kind of familiarity with group theory. If there's any words here you don't understand, we're actually going to sort of go over it in the proof. And I love this exercise. I actually saw it in Martin Isaac's book on algebra, a graduate course. It's a fantastic book. I learned group theory from that book myself. And it's a really beautiful exercise because it uses a lot of cool concepts and a super creative idea. You know, it's really, really creative. So you're going to love that idea when we get into this proof. So we just know that there is this function from G to G satisfying certain properties, and then we're going to conclude that G is abelian. Okay, so we're going to do the proof in 2 steps. Okay, and you're going to see the steps as we go along. So step 1 is the following. We're going to show, okay, so step 1 is we're going to prove that the set of all sigma of x times x inverse such that x is in G, this set is actually equal to G. So you may be wondering why on earth this should matter. Okay, and after you watch this video, you can kind of go over these steps and just think about like how creative this is. So we're going to start off by saying that there is a set equality here. Okay, so how is this going to work? So we're going to do a pigeonhole principle style argument, okay, using the finiteness of the group. So we're going to show that all these elements are distinct, and so when x and y are different, sigma of x, x inverse, and sigma of y, y inverse are different. And so therefore, because there are cardinality G, number of elements in G, elements in here, and G is finite, you know, if you have a subset with the same number of elements, they have to be equal. Okay, so that's the argument. So how do we do it? We have to show that if x not equal to y, then we want to show that sigma of x, x inverse is equal to sigma of y, y inverse. Okay, so let's assume for a contradiction that's false. Okay, so let's say, let sigma of x, x inverse equal to sigma of y, y inverse. Okay, so if sigma of x, x inverse is equal to sigma of y, y inverse, then what we can do is we can put everything to one side. We can put the sigma terms to the left hand side and the other terms to the right hand side. So then we know that multiplying both sides on the left by sigma of y inverse, sigma of y is an element of G, so multiplying both sides by that inverse, sigma of y inverse, sigma of x, x inverse is going to equal to y inverse. Now what we can do is we can multiply on the right by x, okay, both sides. So we get sigma of y inverse times sigma of x is going to equal to y inverse times x, because x inverse x is the identity. So far so good. Now using the fact sigma is an isomorphism, it's a homomorphism. So homomorphisms respect the group law. So sigma of y inverse times sigma of x is going to be equal to just sigma of y inverse times x. Okay, so you can kind of do the group operation inside the sigma, or you can do it outside after applying the sigma. So that's what it means to be a homomorphism. So that's equal to y inverse x. So therefore sigma fixes this point. And we know one of our hypotheses is sigma has no fixed points. Sigma of x is always different from x for all x not equal to the identity. So therefore y inverse x has to be the only exception to this rule, which is the identity. Okay, so therefore we get that y inverse x is the identity, which means that multiplying on the left by y is therefore x is equal to y. So what we've concluded is that the function mapping x to sigma of x, x inverse is a one-to-one function from G to G. Because G is finite, it has to be bijective, in other words, has to be surjective, and so therefore we have this set equality using the finiteness of G. That's step 1. Okay, so now I'm going to do step 2 using the step 1. All right, so far we haven't used the fact that sigma of x equals x, okay, which is sometimes stated as sigma squared is equal to the identity function. Okay, sigma is its own inverse. We haven't used that fact, but we have used the first fact here, and we have used the fact sigma is a homomorphism. So now what we have to do is we have to show that using this, that somehow G is abelian. So how do we do that? So the next thing we're going to do is step 2, is we're going to show that sigma of x is equal to x inverse for all x in G. Okay, so this is actually pretty cool. Sigma of x is actually a very simple function. It wasn't as abstract as we thought it was. It's just the function mapping anything to its inverse. So why is that true? Well, using the fact that G is just all elements of this form, let's apply sigma to something of this form and see what spits out. Okay, so every element of G, Okay, so let G and G, and so we can write using what we just proved in step 1, G equals to sigma of X, X inverse. Now we observe that sigma of G is going to equal to sigma of X, X inverse. Again, using the fact sigma is a homomorphism, it respects the group multiplication, so we can apply sigma to this and sigma to this. So we're going to get sigma of X times sigma of X inverse, just using the fact it's a homomorphism. And so that's now going to be sigma of X is just going to be X because of this property. So we're just going to get X times sigma of X inverse. But here's something cool. What's the inverse of G? The inverse of G, if you invert a product, remember the order changes in groups. GH inverse is H inverse G inverse, okay? Just like with matrices. So what we get is that we get, therefore, this is going to equal to basically G inverse, right? Sigma of X, X inverse inverted. And so therefore sigma of G is equal to G inverse for all G in G, since G was arbitrary. Okay, so I should say this should be like that, sorry. And so therefore we know that sigma of X is X inverse for all X in G. Pretty cool, right? And now we're almost done. Now we're going to show that G is abelian. Step 3 is to prove G is abelian. So why is xy equal to yx? Well, since sigma is a homomorphism, we know that sigma of xy is equal to sigma of x, sigma of y. And because of the concrete definition of sigma, it's just x inverse, what we've proven so far. Therefore, we know that xy inverse is going to equal to x inverse y inverse. But as we said, xy the whole inverse, remember in a group it's always y inverse x inverse. So that means that's equal to x inverse y inverse. And so therefore that implies, what does it imply? That means that any pair of inverses commute, right? But since this is true for all x and y, I could have replaced x by x inverse and y by y inverse, and the same statement would be true. And if I did that, this equation would be yx equals xy. So I encourage you, as just a proof writing exercise, to try to do that from the beginning. So you just want to say that sigma of x inverse y inverse equals sigma of x inverse sigma of y inverse, just applying the fact it's a homomorphism to those elements, and then you would get yx is xy. Okay, so you'd make it a little neater than what I've written down here, but that proves G is abelian. How cool is that? Such a beautiful and creative proof. It takes some time to process and think about how do you come up with this idea and how does it work. I'm a research mathematician and I research group theory. And I've got a whole playlist for you, which is growing rapidly by the day, on fun group theory theorems, eclectic theorems, fun theorems, from basic to advanced. I'm building the playlist. So please check it out here. Click on that playlist, and then you can choose what video you like. On the right-hand side of the video screen on YouTube, you can pick your video, okay? It'll direct you to the first video in the playlist. And here's another fun video you're going to love. It's a bit different. It's a proof that the least common multiple of 1 through n is always greater than 2 to the n. And it's a proof using integration. This is a fundamental statement about the distribution of prime numbers, and it does simple integration that anyone in calculus can understand. It's the most beautiful proof I've seen in math, probably. Check it out here. You're gonna love it. Catch you later. Wish you all the best. Hope you love this video. Please leave a like and subscribe, and I'll see you in the next one.